Today we're going to be talking about proving triangles, proving that they're similar. So I have two examples here, ABC and ABC prime, and we're not worried about the side lengths right now, but we want to notice that the angle for angle A is the same as angle A prime. The angle for B is the same as angle B prime. So when in triangles we have two congruent angles, meaning they're exactly the same, then the third angle is also going to be congruent. Now, we still have to look and make sure they equal 180, because all triangles equal 180 degrees. But if we take 85 and we add 30, we're going to get 115. So these together equal 115. And then if we subtract that from 180, we're going to get the remaining angle of C, which would be 65. So we know if this is 65, this must be 65. So just looking at angles can help us prove whether triangles are similar. So we only need two congruent angles to prove similarity. So let's look at some examples. So we got example 1 here. We have triangle A has a 37 degree. Triangle B, see, does it have a 37 degree? Yes. Triangle A has a 55 degree and triangle B has a 55 degree. So we don't even have to figure out what the missing angle is. We already know that these are similar. So we've proved similarity. We could add these two together and then subtract from 180 and we would find out this is 88. So this has to be 88. Oops, excuse me, 88. So then we look at the second one. We have a 45, great. Now I have a 60 and I have a 75. Those aren't the same, but that doesn't mean that they're not similar. We need to first find out what would be the missing angle missing angle in triangle A. So if we add 45 plus 60, we get 105, and we subtract that from 180, we're going to end up with 75. That makes a perfect triangle. So let's see. Over here, we have a 75. So yes, they are similar. We don't have to find this other one, but if we needed to, because this one's 75 and this is 75, we know that 60 is the only thing missing, so 60 has to be here. All right, example 3. Triangle A has 90 and a 70, and B has 70 to 90. Well, immediately we can look, 70, 70, 90, 90, fantastic. They are all done. Now, if we needed to find the other one, we would take 90 plus our 70. That gives us 160, and 180 minus 160 would give us 20. So we know this would be 20 degrees, and so would this. So those are also similar. So let's look at example 4. We have triangle A and triangle B. We have a 98 degrees, and an 82 and an 82. And you would think, oh yeah, they're similar. However, let's think about this a little bit further. This is trying to trick us. If we add 98 plus 82, that's already 180 degrees. And a triangle can't be more than 180. So there's no angles, no degrees left for this angle. There's nothing that can go here. So we have to have 3 angles. We can't have a two-angled triangle. It's impossible. So this is not a triangle. This is not a triangle. Okay, so it can't be similar because it's not even a triangle. Okay, so let's look further at some sides. So these triangles here, triangle ABC and ABC prime, are similar. And notice that they have different side lengths. Now we've learned previously that things have to be proportional. So if we look and say, okay, what corresponds? So I'm going to use some different highlighter colors here. So AB corresponds to AB prime. Okay, and then we'll use some AC corresponds to AC prime, and then of course the last one, BC, corresponds to BC prime. All right, so we can actually use another little rule for triangles that will help us, that when things are corresponding sides, so think about when the ratio between two sides in one polygon, so we're going to think of this first triangle, when their ratio is the same as the other corresponding sides, then they're going to be similar. So this is what I'm talking about. So let's find the biggest side in this first triangle, and maybe the middle side. Okay, so this is the largest and this is the middle, and then we're going to set that as a ratio. So we have the largest over the middle, or the medium one. So we'll have 5 over 4. So if these are similar based on their sides, then they're going to have the same ratio with large to small. So on this one, we're going to do large, or not large to small, large to medium, large to medium. So we'll do large over medium. We have 10 over 8. Well, they don't look the same immediately, but this to simplify down, 2 can go into 10 5 times, 2 can go into 8 4 times. 5/4 and 5/4 are the same. If you weren't sure and you didn't simplify first, you could say 5/4, compare it to 10 8ths, and remember our cross multiply to see if something's proportional. 5 times 8 is 40, and 4 times 10 is 40. Okay, this will work with any sides. We don't have to just do large to medium. We can do medium to small, small to medium, whatever it may be. We just have to be consistent when we're comparing both ones. So for example, we could do the small and the large. Okay, so we could do small to large, 3/5, and then the other side, small to large, which would be 6/10. This simplifies down. 5 by 2, we get 3/5. 3/5 and 3/5 are the same. So that's another way to prove similarity using side lengths. All right, so let's try this one. This one's not as clear cut sometimes, but these triangles are similar. So I'm telling you they're similar, and if we've got to figure out what this missing side is, we're going to have to think about what we already know. So triangles are so special that we can actually look and see how do we get from one of the sides to the other side? And we only know these two sides, and we know the corresponding one down here. This corresponds to here. And we know that this side corresponds to this side. So basically what we can do, we can say 3 times what got us 6? Well, that's times 2. Okay? So we know to be able to find, because we don't really know scale factor wise, how do we get from here to here? We're going to get a really weird thing. It's not as easy. We don't know necessarily the scale factor that quickly and that easily to see it because of those decimals, but we can easily find it here. So that means that this side is double this side. That ratio is double. So that's why we do 2. So we can take 1.2 and we can multiply it times 2, so 1.2 times 2, and we end up with what the value is here. So you can use your calculator, 1.2 times 2, and we get 2.4. So we can see when they tell us they're similar, and we can go ahead and find the missing piece using something we already know, something we can see. So something that's important to remember is the ratio between two sides in one polygon is the same as the ratio of the corresponding sides in a similar polygon. So that's the way that we just talked about with the sides. All right, so we're going to get into our task today, and we're going to work with a triangle, and you'll see this quotients of sides a little bit better from what we were just talking about. So triangle ABC is similar to triangle DEF, GHI, and JKL. So there's 3 other triangles, and then there's one that's drawn here. And we don't have these other ones drawn, it's just this original one. The scale factors for the dilations that show triangle ABC is similar to each triangle, and they are in the table. So here's our scale factors right here. So ABC is what we see, and its scale factor is 1. So obviously we multiply it by 1, we get the same thing. It's got our short side labeled as 4, our medium side labeled as 5, and your long side labeled as 7. Now, the thing that you have to remember about triangles, these pieces here are your legs. Your longest side is always across from your biggest angle. That controls the angles. All right, so we've already got the first one labeled for us. The DEF triangle is a scale factor of 2. That means it's 2 times bigger than the original. GHI is 3 scale factor, so it's 3 times bigger, and JKL is a half, so it's half the size of the original. So what we're going to do is we're going to use that knowledge, and we're going to find out what our other side lengths would be for our triangle. So if we take the first one, let's say DEF, and we're looking at our scale factor. So we have original short side is 4. Well, if we do it 2 times bigger to get to here, to get to this short side of this DEF triangle, we would say times 2. So 4 times 2 would give us 8. Okay? If we wanted to go 3 times bigger, we would times 3. 4 times 3 is 12. And then 4 times a half, 4 times a half would get us 2. So now we found the side lengths of all of our short sides for our other triangles, our other 3. Now we're going to do the same thing for the medium. So we know that this is 5. So 5 times 2 would give us 10. 5 times 3 would give us 15. And 5 times a half, so we're thinking 5 times a half is the same thing as 5 halves. We can write it as 5 halves. Or we can change that to a mixed number. 2 can go into 5 2 whole times with 1 left over, or we can have 2.5 or 2.5. Okay? And then you'll do the same thing for the last one. So when you do that, you'll end up with 14, 21, 7 halves, or that's the same thing as 3.5. Now, let's go into a little bit more detail. We've already done A, so find the side lengths of the triangles and we'll record them in the table. Now we're going to look for all 4 triangles. We're going to find the quotient of the triangle side lengths and record them in the second table. And we're going to talk about what we notice. So that's the reason we're doing this. All right, so let's look here. So triangle A, and they've done it for us, is the long side divided by the short side. So when we look back up in our original problem here, let's get a little brighter color there. So our original problem, ABC, we had the long side is 7 and the short side was 4. So we're taking 7 divided by 4. So we're just picking 2 sides and we're comparing them. So we're going to do the same thing with DEF. So DEF, the long side is 14 and the short side is going to be 8. Now, we can simplify 14/8 down, and when we do, they can go in, 2 can go into those. 2 can go into 14 7 times, and 2 into 8 4 times. We get 7/4. When we do the same thing for GHI, we're going to have 21 here and 12 here. And we simplify that down. It also simplifies down to 7/4. And then with the last one, you have 3.5 divided by 2, or you can have it as a fraction, 7 halves divided by 2, which is the same thing as saying 7 halves times the reciprocal, so times 1/2, which gives us 7/4. So this also simplifies down to 7/4. So what do you notice about the quotients comparing the long side to the short side in all the triangles? Well, their quotients are all 7/4. So I want you to go ahead and figure out what you would get for the long side and the medium side. So we'll pause for a moment and let you continue. So now we look and see, how did you do? When you did your long side divided by your medium side, you should have gotten 1.4 for all the quotients. They all simplify down to 1.4. And then medium side divided by the short side, you got 1.25 when you simplify them down. And you can do that with the calculator, or you notice they're all 5/4. If you had trouble getting the last one to be the 2.5 divided by 2, that's the same thing as 5 halves divided by 2. And we can think about that as 5 halves times the reciprocal of 2. Then we multiply straight across and we get 5/4. So it's the same thing as 1.25, or 1 1/4. Same thing. So we notice that all the quotients are the same, and the reason is because the quotients didn't change when we're comparing the same sides, the ratios. So when we go back up here and answer, the quotients of the corresponding side lengths in similar triangles are equal. So this is a way to prove similarity. All right, we're going to go on to another question here. So this one, we're given a to find missing side lengths of a triangle is what we're working on in this little section. But the first one, we're given a triangle A, and it has side lengths 2, 3, 4. So we're just going to sketch triangle A, 2, 3, and 4. So we'll just label them 2, 3, 4, and this is triangle A. And then we have triangle B that has side lengths 4, 5, 6. So we know it's bigger. 4, 5, 6. And we're going to call it B. So when we look at this, it's asking, is triangle A similar to triangle B? Now, remember, similar, the angles are the same. I'm giving you the triangle, so we're going to, we're not know anything about the angles. We're looking at just the side lengths. So we can start looking first and say, okay, do I see a clear scale factor? 2 times what would get me 4? Well, 2 times 2, okay, which means that would be the scale factor for all of them. 3 times 2 does not get me 5. 4 times 2 does not get me 6. So I'm kind of thinking, maybe not. But we can't always be completely sure. Sometimes we have decimals and things like that, but I'm pretty close to sure that that's not right. But now let's talk about ratios, how we did last time. So we're going to pick 2. So I'm going to make a little table over here. So we have, for this one, our small side is 2, our medium is 3, and our large is 4. Where this one, our small is 4, our medium is 5, and our large is 6, talking about our sides. So we're going to pick a ratio. So maybe I do, I don't know, medium compared to small. So let's see what that one is. Medium over here is 3 and small is 2. Okay. Medium over here, medium to small, our medium is 5 and our small is 4. Now we're going to compare those. 3 halves, does that equal 5 fourths? No. Let's double check. Let's do a cross. 3 times 4 is 12. 5 times 2 is 10. These are not proportional, so therefore they're not similar. So these are not similar because the corresponding side lengths are not perfect ratios of each other. They're not corresponding. They're not the same ratios between the two. All right, so let's look at a little bit more advanced problem. We got 3 triangles here, ABC, EFD, GHI, and they're all similar. They're telling us they're similar, so we're not trying to prove that. We know they're similar. It says the side lengths of the triangles have some of the units, and find the unknown length. So the side lengths of the triangles have the same units. So what they're meaning here is we got 4 and 4. Okay, so that means if they're all similar, the sides here, they're going to be congruent. So let's look down here. We have 12 fifths, so if this side and this side have to be the same, we automatically know this has to be 12 fifths. Okay? Now, we've got to figure out how did we get 12 fifths? How did 6 fifths become 12 fifths? And you can think about it either way. So we can say 6 fifths times what got us 12 fifths. Okay? If we think about when we multiply fractions, we multiply straight across. So we know we're going to have a number and a number. And at the top, 6 times something gets us 12, and 5 times something gets us 5. Well, 6 times 2 would get us 12, and 5 times 1 would keep it at a 5. So I know that when I multiplied here, this is multiplying by a 2. Okay, so that helps me figure out what it is. So to go from the short side, which we're at the short side right here, to the long side here, I multiplied by 2. So to go from short to long, I had a multiple of 2. And if I wanted to go the opposite direction, this way, from big to little, just like we do scale factor, from long side to short side, I would actually multiply by the reciprocal of 2, which would be a half. All right, so then that knowledge will help us find the other missing sides. So let's go up here to this shape here. We have 4, and that's our long side, and we want to go to our short side. So remember, long side to short side, we multiply by a half. So 4 times a half will give us 4 halves, which is the same as 2. So that value is 2. All right, let's look here at our big triangle. This short side on this triangle is 5, and we want to go to the long side, and we know that E and D are going to be the same, so we just have to find one thing. We know when we went from short to long, we multiplied by 2. So 5 times 2 is 10. That means these are 10. All right, so you're going to have some practice. See how you do.